When you think about it, one of the biggest challenges in all of computing is just how do we organize stuff? How do we arrange information so we can find exactly what we need and find it fast? The answer isn't always a simple straight line. So today, we're going to dive into one of the most elegant and powerful solutions out there, the binary tree.
So, here's our game plan. First, we'll see why a simple list just doesn't cut it sometimes. Then, we'll start thinking in tree structures, building up our vocabulary from scratch. After that, we'll look at the actual code, learn how to get around inside these things, and finally, we'll uncover where these trees are powering the tech you and I use every single day.
All right, first things first. Before we can really get why the solution is so cool, we have to understand the problem it's solving. Why do we even need something more complicated than just a basic list? Let's find out.
Okay, so this slide really gets to the heart of it. With a plain old list or an array, finding one item can be a real pain. You might have to check every single entry one by one. It's like reading a phone book page by page. And the more stuff you add, the longer it takes. But trees, well, they offer a brilliant shortcut. By organizing data in a hierarchy, they can slash that search time, letting us find what we need way, way faster. And this isn't just a small tweak, it's a completely different level of efficiency.
Okay, so we've seen the problem, now let's jump into the solution. This is where we need to shift our thinking a little bit. Not in straight lines anymore, but in these branching structures. And to talk about them properly, we all need to be using the same words. So let's build our vocabulary.
Honestly, the best way to picture a tree is, well, like a family tree. It's a perfect analogy. You've got ancestors and you've got descendants. Information flows down and branches out. But here's the key. It never, ever loops back on itself. If you can keep that simple idea in your head, you've already grasped the core concept.
So what are these trees made of? They're made of things called nodes. And a node is really just a box. That's it. It's a container that holds one piece of our data. It could be a number, a word, pretty much anything.
You know how every family tree has that original ancestor at the very top? Well, in our data structure, that's called the root. It's the one single node at the very beginning of it all. It doesn't have a parent, and it's our starting point for the entire tree.
So if the root is the start, the leaves are the end. Makes sense, right? A leaf is just any node at the very bottom of a branch. It's a dead end. It has no children of its own. So now we've got our basic building blocks: the root, the nodes, and the leaves. Now that we're all speaking the language of trees, let's get a bit more specific. See, there are lots of different kinds of trees out there, but we're going to zero in on one of the most important and fundamental types, the binary tree. And this is where we get to peek at the actual code. The rule that makes a binary tree binary is incredibly simple. The name kind of gives it away, right? Binary means 2. So in a binary tree, any given node can have 0 kids or 1, but at most 2. And we give them specific names, the left child and the right child. That's it. Seriously, that one simple rule defines this entire powerful structure. So how does this actually look in code? Let's use C++ as an example here. We'd start by defining a blueprint for a single node, and we do that using something called a struct. Just think of this as the architectural plan for one of those boxes we were talking about.
Now, our little blueprint needs a couple of things. First up, a place to actually store the information. This line right here, int data, basically creates a little pocket inside the node to hold a value. And second, and this is the magic part, we need a way to connect these nodes together. These two lines create what are called pointers, which are pretty much just arrows. So every node we create gets 2 of these arrows, one that can point to a child on the left and one that can point to a child on the right. This is literally how we build the branches of our tree.
Okay, so we've designed the blueprint, we've built the structure, but what good is a library if you don't know how to find any of the books? So the next question is, how do we actually move through the tree to read the data that we've so carefully stored inside? This is the big question, isn't it? We've built this cool branching structure, but how can we guarantee that we visit every single node in an organized way? We can't miss any, and we shouldn't visit one twice. Well, the answer is a process called traversal. Traversal sounds like a fancy word, but it's really just a simple idea. It means having a clear set of rules for walking through the tree. It's our methodical game plan to make sure we see everything inside our structure and see it exactly one time. So there are 3 classic ways to do this, and they all have a simple pattern. It all comes down to when you visit the root, the parent node. With in order, you visit the root in between the left and right sides. With pre-order, you visit the root before you go left or right. And with post-order, you guessed it,
You visit the root after you've explored both of its children.
Now this table right here, this is your cheat sheet. It's a huge takeaway, because each of these traversal methods has a very specific and very powerful use case. For instance, if your tree is a special type called a binary search tree, using an in-order traversal will spit out all the data in perfect sorted order. It's amazing. Need to make an exact copy of a tree? Pre-order is your go-to. And for safely deleting nodes without messing things up, post-order is the way to do it. The order you choose really, really matters.
And you know what the best part is? All of these methods are incredibly efficient. This notation here, O of n, it just means that the time it takes to run is directly related to the number of nodes, which is n. Since we have to visit each node just once, well, it's literally as fast as it can possibly be. You can't beat that.
So, we've gone from the big idea all the way down to the code. But let's bring it all back to the real world. Why does any of this matter? Why have we spent this time learning about nodes and pointers and traversals? Well, it's because this exact structure is hiding in plain sight, running the technology you rely on every single day. Seriously, think about it. The folder structure on your computer, that's a tree. You've got a root folder and then folders inside of folders. How do databases find your information in the blink of an eye? They use tree-based indexes. The AI that helps make a decision, the compiler that understands your code, even the web browser that's figuring out how to display a web page, they are all using trees under the hood. It's absolutely fundamental to modern computing.
And this quote, this really gets to the beautiful elegance of why trees are so powerful. The structure just repeats itself. If you take any branch of a big tree, that branch is, itself, a smaller tree. This self-similar pattern makes them a perfect fit for a programming technique called recursion, which lets us write incredibly clean and simple code to solve really complex problems.
So remember, a tree isn't just some abstract computer science thing. It's a basic pattern for organizing information. Now that you know what to look for, I bet you're going to start seeing it everywhere. So, where do you think you'll spot the next one?